So this is the lecture 21st and 22nd combined. Last class I was trying to tell you that as far as Euler's second axiom is concerned, it is challenging to handle the algebra involved therein. Euler's second axiom is what I am showing here. It involves on the left hand side first finding an expression for the angular momentum of an RB with respect to a point O which is fixed to I, and then taking the time derivative of that, and that time derivative is equated to the net moment of due to all the forces that are acting on my RB about this point O. Calculating the right hand side is not challenging, it is rather straightforward. It is here the left hand side which will pose several challenges. And thus I was telling you in the last class there are three things we will learn before we reach a position of solving Euler's axiom for some problems of interest. The first thing that we have to learn is to derive a modified form of the Euler's second axiom, which I refer to using this acronym MESA, Modified Euler's second axiom. Modified Euler's second axiom will set us free from the restriction that this point O, about which we are computing the angular momentum of the RB, that point has to be fixed in O. So in the original Euler's second axiom, that point has to be fixed. In modified Euler's second axiom, we want to set ourselves free of that constraint such that the angular momentum can now be computed about any point A, no restriction whatsoever, right? I was doing this derivation last time. We will go to that derivation and complete it, right? So the modified Euler's second axiom is this expression, final expression. You see on the left hand side we compute angular momentum about any point A, take its derivative with respect to an inertial frame. Right hand side I have moment due to all the external forces about this point A, and then there is an extra term which involves what? RCA, the position vector of the center of mass measured from this point A. It involves of course the total mass of the RB. So M is the identity of the RB as well as the total mass. And then there is a term AAI. AAI is the acceleration of point A with respect to this frame. To prove this, I took the first step and derived a relationship which is shown here. What is this relationship? In this relationship, I am trying to express the angular momentum of this RB about point A, no restriction, with respect to a frame F, and that I want to write as angular momentum of the same body about its center of mass and with respect to frame F, and then an extra term which is mass times RCA, position vector is shown, cross product with VCAF. VCAF is velocity of point C relative to point A with respect to frame F. This I did prove. I did complete this proof in the last class. And I want to remind you again that this particular proof or this particular relationship holds good for any frame F. Whereas Euler's second axiom, or that for that matter the modified version, they require the reference frame to be an inertial reference frame, not this relationship. It is generally true. Okay, so this I completed. Now I will use this relationship to move further and try to prove MESA. Okay. So since this relationship, let me call it as star. So that's a straightforward argument that since star is true for any frame F, it must be true for an inertial frame as well. And thus I can write star as let me call this equation number 1. Another argument that since 1 is true for any point A, no restriction, it must be true for O as well, and O is this point fixed in I. So I get another equation let's call it 2. Okay. I'm going to subtract 2 from 1. When I do that, HCI will drop out. I will get this is what I get. Right? Let's call it 3. Now I'm going to take a derivative of this equation with respect to frame I. Before that, let me take HOI on the right hand side. let's call it 4. Now we take time derivative both sides. Left hand side I get so if you compare the left hand side of this last equation with what we want to prove, actually this is what we want to prove. I already have the left hand side ready with me. Left hand side here is just the rate of change of HAI that I already have now here. So I have to work on the right hand side. This is the time derivative of this term, and then I have one more term with respect to I. This here also with respect to I. Okay. Now this term, rate of change of, it's important to put this with respect to I. If I am not writing that, I am making a mistake. This with respect to I should be appearing in each and every term, because everywhere I have a vector, and rate of change of a vector depends on the frame. I must specify the frame. Now this term here is Euler's, well, let me call this term as alpha, this is beta, and the third term as gamma. On the right hand side I have three terms, alpha plus beta plus gamma. Let's also put vectors, because after all these are vectors. Okay. Now note that alpha vector this is actually equal to MO, Euler's second axiom, which we are assuming to be true. Okay. Let's look at beta. Beta is time derivative of M is a constant, doesn't change with time, but then there are two terms here. Right? Now, time derivative of RCA with respect to I is nothing but VCAI. Time derivative of position vector gives us velocity vector. and then time derivative of BCAI will give me ACAI. Where is acceleration, and you know the meaning of, I hope you know, you are comfortable with this notation ACAI. It is the acceleration of point C relative to point A and with respect to I. Okay, so here we have the same vector having a cross product with itself, so this is going to vanish. The only surviving term in beta is this. We will keep it for the time being. Now if you go and look at gamma, gamma is a constant, and then you apply time derivative once to RCO, once to VCO, you will get two terms. Right? This gives me M VCOI cross VCOI minus M RCO cross ACOI, which is this term. This again will vanish. You have gamma as minus on MRCO cross ACOI. Okay, so now if I assemble gamma from the next slide, beta from here, and alpha from here, and put all of that back in this equation here, which I call as equation number 6, I get MO what did I have here? RCA, ACAI. ACOI. Okay, so I just focus on the right hand side. Mind you, ACOI is same as ACI because O is a point fixed in I. This is the RB. So AOI is always 0, right? So that's why I am replacing ACOI by simply ACI. Okay. Yeah. I have taken this term here, MRCA and the other two terms which have ACI, I have brought them here. Now, we can write, maybe I go to the next slide. Now I can write, referring to the figure on the right hand side, I can write RAO vector as RCO vector minus RCA. RAO vector equals RCO minus RAC minus RCA. Now if I use this here, I should be able to write this is what I wrote, and then these two terms I will combine, use this and write that as minus MRAO cross ACI. Now I know following the steps from one slide to another one may be a problem right now as you are watching the screen, but when you go to your hostel room, try deriving it and I'm sure it will make sense. So this is the equation I get. Now Euler's first axiom tells me that the resultant force or the net force acting on the body must be equal to this. What's the net force? So let me put the net force here. It's an equivalent force system acting at point B, and let the torque here be CRB. So FR and CRB make the equivalent force system acting on the RB. Right? So I can replace this by FR. RAO crossed with FR, and then this extra term. Okay. RCAI. All right. Now I am going to combine these two terms. So what is MO? MO is the net moment due to all forces, external forces, about point O. So given that the force system has FR and CRB, MO, what should be MO? MO should be R BO cross FR minus CRB. Alright. Therefore, MO minus RAO cross FR will be what? Will be RBO cross FR minus CRB minus RAO cross FR. Now let's focus on these two terms, RBO minus RAO. So A is a point here, this is the position vector RAO. This is point B, this is the position vector RBO. So I have here RBO minus RAO cross FR minus CRB which is what? RBO minus RAO will be RBA vector cross FR. Okay. This should be plus. It's plus CRB. RBO BA plus FR plus CRB. RBA cross FR plus CRB can be written as, this is what is exactly equal to MA. It is the net moment due to all external forces about A. Okay. So I have shown that this thing is MA. Now come back here. I call this equation as 2 star. this must be Ma. This is what I have just proved. Okay, so the conclusion is this is what I wanted to prove. It's a long proof. I've already said a couple of times. It's important. This is the modified Euler's second axiom. Okay. Now, so one item that I wanted to learn before solving Euler's second axiom, I have completed that. Coming back to the first slide, handling Euler's second axiom, first part is done. We have derived the equation where angular momentum is taken about point A. Two more things to learn. What is the second thing I want to learn? Handling Euler's second axiom, second thing to learn. Now let's refer to this diagram. RB, same RBM. A is a point fixed in M, and this is the reference frame F. The second thing I want to learn is to be able to express the angular momentum of the RB about point A with respect to frame F in terms of two different quantities. The first quantity that I want here is how mass is distributed in space. As far as the RB is concerned. And the second thing I want here is angular velocity. Angular velocity of RB. Remind yourself that the definition of angular momentum of the RB about this point A with respect to frame F will be this integral. This is the definition of angular momentum. Inside this integral, you see three types of quantities. What are these three types? First is position vector of a typical point. Second is velocity of typical point P relative to A and with respect to frame F, right? And the third type of quantity is, of course, mass, material mass, mass of the RB material. So the way we have defined the angular momentum of a body, here it is mixed up, all mixed up in this integral. If one wants, one can compute this. If one is always ready to compute the integral in this mixed form, he can always go ahead and do that. Again, doing this kind of integral every time is complicated. Not impossible, but algebraically it is complicated. And remember that in Euler's second axiom, it's not only the angular momentum that is going to appear, but it is the rate of change of angular momentum. What does it mean? It means that even though if you are ready to compute that integral for a given instant, that is not enough. For the very next instant also you will have to repeat this computation of the integral. So it is a very tedious task. This is the kind of challenge I have been trying to mention for last two classes. And that is why what we want to do now is to see if it is possible to split angular momentum of the body into two parts, where one part is dependent on how mass is distributed in space, and the second is the angular velocity of the RB with respect to F. Is it possible to do this? If it is possible to do it, then the convenience would be that this part you can compute for once and for all. You do this computation for once and you can use it for all time instants. Angular velocity of course can change with time, and we will handle that, but not repeating this computation for every time instant will be very, very convenient. Okay, thus we want to set it like this. Now keep in mind that this kind of splitting is possible. This splitting is possible only when body is rigid, which in our course is true always, and A is part of the body also. If you are not paying attention in the class, be assured that you are going to miss these fine details which I really like asking on multiple choice questions. So these two conditions should be there, only then you will be able to split it. Alright. Now this splitting is going to be something like what I am showing on the slide, on the top of the slide. If the body is rigid and this point A is fixed to M, you can write the angular momentum of the body in this form. There is a dot product on the right hand side. The dot product is between the angular velocity of the body with respect to frame F. We are familiar with this quantity already. The other quantity with which the dot product is happening is a second order tensor. Second order tensor. That second order tensor I am representing by the symbol I superscript A, and that superscript A has to do with the fact that we are trying to find the angular momentum of the body about this point A. Then I put a double underbar. Double underbar means it is a second order tensor. So this is a peculiar splitting that is happening. You left hand side you have a vector. On the right hand side the dot product is happening with a vector omega mf, and the other participating quantity in the dot product is the second order tensor. This second order tensor is called the inertia tensor of the body at point A. Inertia tensor of the body at point A. Now you might be familiar with this word inertia. You might have come across this word in context of moment of inertia earlier. Indeed, this inertia tensor has something to do with what you know as moment of inertia. But inertia tensor on its own is much bigger than what you know as a moment of inertia. It's a bigger quantity. It will turn out that what you know as moment of inertia is a small part of this whole inertia tensor. We will study this inertia tensor in detail. But before I explain to you what is the inertia tensor of RB at point A, I want to tell you briefly what is a second order tensor. For that matter, what is a tensor itself? The moment I say the word tensor, probably the quantity that will come to your mind is the stress tensor. You have some idea it is force per unit area. Indeed, stress is the second order tensor. But what is a tensor in general? And what is a second order tensor in general? Let's first have some answer to these two questions, and once we have some idea of a second order tensor, I will come back to the inertia tensor itself, which is relevant for this equation. Before that, there is one more point I want to make. IAF, there is no F here. IA double under bar, I call it as inertia tensor of RB at point A. A is part of, A is a point fixed in M. I am worrying about inertia tensor of the body at A because I want to know the angular momentum of the body at about A, right? But suppose one is not interested in HAF, one is interested in finding HBF, where B is another point which is fixed in M. So if you want to know the angular momentum of the RB about point B with respect to F, you can write a similar equation, or you can do a similar splitting, and that splitting will be like this. Now in this splitting, omega mf is the same as before. Same angular velocity. After all, every rigid body has a unique angular velocity. That is not going to change whether I try to find angular momentum about A or about B. Why would the angular velocity change? Doesn't change. What changes here is now, if I want to write angular momentum of the body about point B, I should have another tensor here, IB, two under bars, and this will be called inertia tensor of the same RB at point B. And do keep this fact in mind that in general the two tensors are not the same. They are not the same. So in that way, you go to any point Q, you will have a quantity which will be this. Every point of the RB will have its own inertia tensor. This inertia tensor is of the same RB at point Q. Okay. Now let's answer this question. A tensor of order n. This is the mathematical definition of a general tensor of order n. Inertia tensor is the second order tensor, but tensor can be of any order, where n goes all the way from 0 or 1 or 2 or any number, any positive integer including 0, so I should say any positive whole number. How do we define it mathematically? So this I have gotten from a book. This text that you see here, it does look very wordy, but this is the smallest description I can have to describe what a tensor of order n is. To the best of my ability, I do need all these words. I'll read it aloud once. I don't know whether this is very clear on the screen or not, but it should be clear enough on the PDF file, that I am very sure. A tensor of order n. A tensor of order n is where n is any number, any whole number, in a three-dimensional space. In a three-dimensional space. We live in three-dimensional space, so I am talking only about a tensor of order n in three-dimensional space. Again, mathematically one can define a tensor of order n in any m-dimensional space as well. M-dimensional space. I am not bothered about m-dimensional space. I am only concerned about three-dimensional space right now, because all mechanics, motion of objects is going to happen in three-dimensional space, classical mechanics. So a tensor of order n in three-dimensional space is a mathematical object comprised of 3 raised to the power n numbers. 3 raised to the power n numbers, the numerical value of which may depend on the coordinate system we choose to express that tensor. The numerical value of these 3 raised to the power n numbers will depend on which coordinate system you use. These 3 raised to the power n numbers are called the scalar components of that tensor in the chosen coordinate system. Even though these scalar components in general are dependent on the choice of the coordinate system used to express it, the tensor as a mathematical entity and the physical quantity that it represents must be independent of the choice of the working coordinate system. In other words, the tensor itself is invariant to the choice of the coordinate system being used to express it. This property of the invariance of the tensor is ensured by a set of relationships that exist between the set of 3 raised to the power n components of the tensor in one coordinate system and another set of 3 raised to the power n coordinate components of the same tensor in the other coordinate system. Right? Such relationships are called the transformation rules of tensors. A tensor of order 0 is a special case wherein the transformation rule is trivial. Such a tensor is described by only one number. After all, 3 raised to the power 0 will be just 1. And since it is described by just one number, this is a special case in which you go to any coordinate system, that component of the tensor will be independent of the choice of working coordinate system. Alright, so if you have a tensor of order 0, that is called a scalar. If you have a tensor of order 1, we have a special name, vector. If tensor is of order more than equal to 2, we just call them tensor of order n. For example, stress is a tensor of order 2. Inertia is a tensor of order. Inertia of an RB about a given point on it is a tensor of order 2. Now, if we are dealing with a second order tensor, inertia tensor, how do I express it in a coordinate system, in a Cartesian coordinate system? How do I express that in a Cartesian coordinate system? I stop here for a break. We will meet.